reason. Okay, so recording started. So let me share my screen. Okay, only 50 students are present. The class strength is 90 plus. So this is not acceptable. If you continue like this, then maybe I'll stop sharing the recorded lectures later, or I'll start. Just 1 minute. Some echo is happening. In that case, I'll stop sharing the recorded lectures. Plus, I'll start taking the attendance also. So please inform it to the other people also that recording attendance is must. There are 90 plus students, and I can see only 50 or 51 students. So it's almost 30 or 50, or 40 students are absent. Okay. So from last 2-3 lectures, we are discussing about the basic concept of computer. So I'll hope today I'll complete this basic introduction so that from next week I'll directly start from the textbook. And in this weekend I'll share a video also with you. So that video you can also consider as a course content. Why? Because we missed 2 lectures. So for adjusting these 2 lectures, I will upload one recorded video. You have to watch that video before starting the next lecture. Means before starting next week, you have to complete that recorded video also, because that recorded video is also a part of how computer works. So this week I'm completing all the basic introductions and all, and from next week I'll directly start from the textbook. Okay. So last class I stopped here and I explained you that computer only understand a machine language, but machine language and assembly language are almost similar. So we'll assume that computer understand assembly language. And I have also explained that the assembly language are different ISS, different assembly language. So different computers may be designed on top of different assembly language program. Okay, so those things will discuss again when I will start discussing from the textbook. And the last class I also show you a demonstration that how if you have written a C program, then when you will compile the C program, how the assembly language code is generated, and then those assembly language codes are actually executed on a computer, not your C program. Okay, so that part was also I have discussed. Now the next question is, if you remember this example, I've explained that suppose you need to perform this operation R equal to A plus B plus C, then how computer will execute? So for that, computer will execute this set of instructions, this program actually in CPU. And one by one, when this instruction will be executed, at the end of these instructions, this complete operation R equal to A plus B plus C will be completed. That I have discussed in last class. And I've also explained that how to generate this type of assembly code, right? Because if you have written a C code, who generates those assembly code, that I've also explained. But then now next question is how this program executes in CPU. So this is the next question. So normally when you write a code or when you write a program, suppose if you remember my last lecture, I have written a program called p1.c. So that program is also stored in memory. Suppose after writing that p1.c program, if I shut down the computer yesterday, and if I now start that computer again, I'll get this p1.c file there, right? So it means that when you will write a program, the program is also stored in the memory. So I'm not differentiating it here that memory means hard disk or anything, but yes, it is stored in memory, right? So now if I compile the program that p1.c to create a.out file, which is the executable file, that will again store in memory. It is not stored in computer in CPU. So how those instruction will be executed in CPU? Because in last slide I said that the instruction will be executed in CPU, and based on this execution, your R equal to A plus B plus C will be executed. But here we can see that in actually the program that will write, or the set of instructions that will write to execute on the CPU, are also stored in memory. So here that this is the scenario I have explained here. You can see the memory is divided into two parts actually here. This part is storing all the instructions, or your program is stored in this part, set of instruction, and this part the data is stored. Okay, so now if you want to execute a operation like this, R equal to A plus B plus C, which is actually written in this program, suppose. So now how to perform this operation? Here most probably it is like A R equal to A plus B. First of all, you have to move these instructions one by one to computer, to the CPU. Means first you need to move these instructions from here to here one by one, and then you have to perform the execution. So you have to understand this point, that initially your instructions and data both are in memory. So how you will move this instruction one by one to CPU? I have not written. I think this is your CPU or processor, and this is your memory. So for this, there is a program counter. There is a PC here. You can see this is called program counter. This is a special register. Initially, assume that initially the value stored here is 1000. How it will store that we'll discuss later. But at this moment, you assume that the program is starting from this address, like 1000. From in 1000, from this address, your program is stored in memory. So assume that the initial address from where your program starts is it is loaded in program counter. Who loads this in program counter, that I'll not explain today, but you assume that the first address is loaded in program counter. So if the current value of program counter is 1000, it means that go to memory location 1000 and fetch that instruction. So here we'll say which instruction. This is the first instruction. So the first instruction will be fetched from here to here. That is the load instruction. Load $1 and then $0. That will be fetched from memory to this register. This is instruction register. Okay, and then this instruction will be executed. So after completing this execution of this instruction, the program counter value will be incremented by 4. 1000 to 1004. Why 1000 to 1004? Because next instruction is stored in 1004. Why? Because we're assuming that each instruction takes 4 bytes. Okay, so next instruction is stored in 1004. So now if the program counter value is 1004, it means that I have to go to memory and fetch the instruction which is stored in 1004, which is this instruction. So the next instruction will be now moved from this location to this register. This is called instruction register. And after fetching the instruction here, this load is, I'm not writing the complete instruction, that just writing load. So after fetching the second instruction here, again the second instruction will be executed here. And after executing, a program counter value will be again changed from 1004 to 1008. So after this, once this instruction will be completed, then we'll go and fetch the third instruction. In the same manner, we'll go and we'll fetch the third instruction. Why? Because program counter value is now 1008. So this instruction will be fetched here and it will be executed. So this is the procedure. This is how your program executes. Initially, the first value of the program counter will be from where your program is beginning, and then one by one your program counter values will be incremented after executing every instructions. And in this way, all the instruction that is written in the memory or for this particular program will be fetched to the CPU, perform the execution. Okay, so now the next question is, we are fetching the instruction. When will fetch the data? Fetching the data is depends on instruction. If you remember in last class I said interaction data communication with memory is means if you have written a program, that program will only communicate with memory through the load and store instructions. So if you fetch a load instruction here, then maybe this load instruction is again saying that load content from this memory. At that time I will go to this part, this memory, this data part, and will fetch the data from this memory to a CPU. That I'll explain in more detail in next slide. Okay, so I think the concept of program counter is clear. So program counter increments every time after executing instruction, it increments by 4. But do you think every time it will go, program counter will increment sequentially, if you consider the example that is written in right side, that is this example here, the program counter will first point this and instruction, then it will point this instruction, then this, then load, then the third add instruction, and the store instruction. It is pointing all the instructions sequentially. So every time it will increment by +4 +4 +4 like this. But that's not the case every time, right? If you go to and if you check this particular program, then first program counter will be here, then second program counter will be here, then third program counter will be here. After that, this is actually a branch instruction. Branch instruction, we'll discuss more about branch instruction in this course, but here you can consider it like this. Suppose you have a C program like this, A equal to B plus C, and then if A greater than 50, you will be here like A plus plus, else B plus plus. If this is a C code, then after executing this line, you will execute this line if sequentially. But after executing this line, second line, it is not guaranteed that which line you will execute. Either you will execute this, that is sequentially the next line, or you may need to jump to this line also, right? Because of this condition. So same way, this is a branch instruction here. So branch instruction means here we'll check the value of these two registers, $1 and $2. If these two registers are same, then will not jump. Otherwise, we have to jump to this else. Else means here. So after this executing these instructions, we have two options. Either we will start executing from here or we will start executing from here. So in that case, program counter may not increment every time sequentially. So all these things we'll discuss in this course, that if you have a branch instruction, this instruction is branch instruction, then which instructions are next to be executed. Means a program counter will be incremented either by +4 or plus something else. So this is a very important area of research. It is called predicting the next instruction when you are executing a branch instruction. This is an open area of research. So we'll discuss about some basic concept of the branch prediction and all, but that maybe after 2-3 weeks. Okay, here the only thing that you need to understand is what is called program counter, how it works, and every time it may not means increment sequentially. If you understand this point, then it is enough. Okay, now we'll go some more technical details. Till now, what I've explained you that if we have instructions, then based on the program counter values, one by one, we'll fetch the instruction to computer and we'll execute it. So suppose 1000. So based on 1000, we'll fetch the first instruction here. This is load $2 $0 that will be fetched here and will execute it. But the next question is how computer will execute this instruction. What are the internal steps to execute an instruction? In this slide, we'll try to understand this. But for this, we'll start with add instruction. So what we'll assume that the program counter value is suppose now 1008. So in this case, which instruction will fetch? Will fetch this add instruction. So suppose add instruction will be fetched from memory to processor, and in processor there is a specific register called instruction register where you will store the instruction. This is the first step. This is called fetching the instruction and storing it in a register is called fetch of CPU is called fetch. After fetching an instruction, next step is called decoding step. In decode step, what we will do, we'll decode the instruction. Sorry, I think two important points need to be discussed. Otherwise, maybe some of you will face issue. So I'm pausing this discussion here just for 5 minutes, and quickly I'll explain one important point. That in last class I said that computer only understand the binary numbers, right? So some important things are required here. What is called bit? Bit means either binary 0 or binary 1. Binary 1 or binary 0. This is called bit. Then what is called byte? Byte normally we will represent as capital B is 8 bits, right? And what is called then kilobyte, KB is 1024 bytes. And what is MB is 1024 KB. And what is GB is, it is 1024 MB. I hope all these things are known to you, but still I'm explaining it here. Bit mean either binary 1 or binary 0. Then byte mean 8 bits. KB means 1024 bytes, MB means 1024 kilobytes, and GB means 1024 megabytes. Okay. I hope you know this concept, but maybe this concept will be required in this slide as well as in next slide. That's why I have explained it here. Now I'll again go with fetch. Fetching is done. Now we'll go for decoding. So as I explained in last class also, actually the instructions are stored in memory in binary format, actually in machine language format, right? They're not stored in this format like add, like not in English way. So why I have also explained that in this entire lecture will assume the instruction in this format only, so that we can it will be easy to understand. But in reality, this add instruction is actually a 32-bit binary information. So some bit here will be reserved for writing this part. This is called opcode part, which we will discuss more when we'll start understanding the start reading the textbook. Then there will be some bits will be reserved for this first register. Then there will be some bits reserved for this second register and then third register. So the total there will be 32 bits, like binary bits, 1 1 0 0 1 1 0. All the combination of bits will be there. This is the 32 bits will be there like this. And we are moving this combination of 32 bits from 108 location to here. So maybe I have written it like this add, but you have to understand that it's just a combination of binary bits. Okay, so now what we perform in decode stage? In decode stage, we know that here that up to this part, this the add is written in this. So these fixed bits will be read, and based on this fixed bit, the computer will understand that okay, it's a add instruction, or it's a load instruction, it's a store instruction. So in decode phase, we'll decode the instruction, will decode the instruction that is stored in instruction register, and will try to understand, the computer will understand that okay, it's a add instruction. The moment computer will understand that it's a add instruction, then the computer will also understand, since it's a add instruction, it must have two register, source register, which information I need to add, and then I need to store it in a destination register. So the moment in decode phase, computer will understand that this is a add instruction. At the same time, it will also understand that this instruction has a destination register, which is $1, and two source register, $2 and $3. Okay, so all this information will be gathered during the decode phase, and these informations are already available in this instruction that I have fetched. You no need to fetch any other information. Now the second thing, this is also done in the decode phase. When the computer will understand that it's a add instruction, so it means that it need to, in the next stage, it need to perform a addition of the content, which two registers, content of register 2 and register 3 need to be added. So at the end of this decode phase, what it will do, it will read the content of register 2. So this is register 2. So value of register 2 will be available in a temporary register like this, and the value of register 3 will be available here in this temporary register, suppose. So all these things will be performed in decode phase. And also in decode phase, since the computer realized that it's a add instruction, it will also send an instruction to this unit, arithmetic logic unit, that perform a addition. So all these things will be performed in decode phase. This is called decode. In decode phase, what we are doing, first we decode the instruction, not we as computer, decode the instruction. After decoding the instruction, computer will realize that it's a add instruction. Then once it realizes the add instruction, it will also realize that it needs two source register. So which are the two source register? Register 2 and register 3. So it will go and read the content of register 2 and register 3 and store it in some temporary registers. Okay, and it will also generate a signal, because it's a add instruction, so it will also generate a signal for this ALU to instructing this ALU to perform an add operation. All these things will be done in decode phase. The next phase is execute phase. In execute phase, these two values of these two registers are already available here, right, in here. So in this phase, the arithmetic logic unit will only perform this addition. How arithmetic logic will perform addition? Because arithmetic logic unit has capability to do some other operations also, like subtractions, multiplication. But why in this case arithmetic logic unit will perform addition? Because in the previous phase, in decode phase, computer has already instructed ALU to perform addition. See, so in this phase, execution phase, ALU will perform the addition and result. Suppose result is here. So this assume that this is again a temporary register or a latch where the result is stored. Execution phase is done. The next phase is memory. This is not required, so I'll not explain here. After this, the last is write back. I'm writing only WB. You have to understand this write back. So last phase is write back. So now again check the instruction add. What this add instruction is saying. If you look here also, add means add the content of register 2 and register 3. And once this result is ready, where to store the result? We need to store the result in register 1. So that is called write back. So here now if you see in arithmetic logic unit, after the execution phase, your results is ready in a temporary register, right? Now the write back phase, you need to store this result back to register 1, which is register 1 here. It will be stored here. So all these things will be done. So if you fetch an instruction, after fetching the instruction, we first decode it. Not we assume that whenever I'm saying we, you have to understand it's a computer. Okay, so we first off we decode it. After decoding, then we'll go to the execution phase. After execution, we go to write back phase. When the result is ready, we'll write it back to the destination register. If this is done, this is clear, I will now explain you one more instruction. Or the execution steps of all instructions are not same. Now let us discuss about a load instruction. So assume that the program counter value is now 1000. If the program counter value is 1000, then which instruction it will fetch? It will fetch the first instruction, which is a load instruction. So let me write the load instruction here. So I have written a load instruction here. So again, the first point is fetching. So fetching is already done because I have already written the instruction in instruction register. This is called instruction register. So fetch part is done. Fetch again. So now after fetching again, we have to understand that whatever we fetch and whatever is stored in instruction register, it's a binary bits. It's a binary combination. And from this bits, there is some fixed position here based on which we can understand that what is the opcode. Opcode means it's the add or load or store. Which type of instruction it is. So based on this bits, the computer will understand that okay, it's a load instruction. The moment it will understand it's a load instruction, it will also understand what is the purpose of a load instruction. The purpose of a load instruction is, we'll understand it from here. Let us concentrate on this load instruction. What this load instruction means, loading some data from memory to CPU. I think I have explained it in last class also. Load instruction means loading some data from memory to CPU. So which data? This is saying load, go to this memory location and read the content of this memory location and store it in register 2. So what is this memory location? This memory location is actually 0 plus register 0. So in last class also I said that assume that the base register, base value, that is 12,000 is the base. 12,000 is already stored in register 0. That's why they have written 0 plus register 0. Okay, so this is what this load instruction is saying. Let me write it again. Okay, so fetch done. In decode phase, the computer will realize that it's a load instruction, so I have to go to a specific memory location and fetch a data. So the first question is which memory? This is the memory. So decode stage, it will send a add instruction here, and it will also read the register 0 here, and this 0 value will be here. I'll explain why. All this thing will be available at the decode phase. Why? Because in execution phase, first of all, we need to calculate the address, because the address is currently written in this format. So first of all, we need to perform this 0 plus register 0. So this is a add operation, right? So that add operation will be performed by arithmetic logic unit in the execute phase. So what we need to prepare in decode phase, first of all, we need to, if it is a load instruction, this is the source register. This is the source register. Source register is register 0. So the value of register source register should be available here in this temporary register, and this is a constant 0. The value of this 0 will be available through this register, suppose, and it needs to perform a add. Okay, so this everything will be set in the decode phase. When it will come to execute phase, this 0 plus register 0 will be calculated, and your results is ready here. What is this result? This result is actually an address, which is normally called effective address. So what this result is saying, this address in memory and collect the data. So this address will be actually 12,000 this now. So from here we'll go to this address. This is the address. We'll fetch the data. We'll fetch the data. Now data is here. Now where to store this data? Now look at the load instruction again. If you load the load instruction, it is written that read the content from a memory location and store it in register 2. So when the data will be loaded in the CPU, it will be stored from here to register 2. So this is how a load instruction operates. So now I think I missed 2 points. After execution phase, when it after execution phase, your effective address is ready. That part I've explained. After this part, when it is the next phase is memory phase, memory access phase, MEM. In memory access phase, this instruction will go to memory and fetch the data to the computer, to the CPU. This is the memory phase. And after once the data is already available in computer, where to write the data, it is again the write back phase in load instruction. So let me remove all this thing and I'll again quickly explain the load instruction. This whatever concept I'm discussing today, this will be required throughout your course. Okay, so now how load instruction will work, again I'm explaining it. First we will fetch it. So assume the instruction is already there. After this, when we'll decode, the computer will realize it's a load instruction. So first thing is we need to calculate the effective address. So to calculate the effective address, we need two things: constant and a source register. So these two values should be available here during the decode phase. So in decode phase, these two values will be register 0 will be available here and the constant 0 will be also available here. So decode phase done. In execution phase, the computer will calculate the effective address, that is 0 plus $0, and after execution phase the effective address will be ready here. The next phase is memory access phase. In memory access phase, we will go to this particular memory address here and will fetch the data to the computer. This is done in memory access phase. We are accessing the memory here, and after that the next phase is write back phase. In write back phase, the fetch the data that we already moved will be stored in a particular register here. So this is how a store instruction works. So maybe you can see the difference. There is a difference between executing a add instruction and executing a store instruction. What is the difference? If you see the add instruction, the add instruction is not interacting with memory. If you remember when I was explaining add instruction, I said first it will go fetch, decode, then it will execute and then write back. I said memory is not required, because memory access is not required in add. If you concentrate on a add instruction, this is saying add the content of 2 register and store it in another register. There is no question of memory here. That's why this point is important. Anytime if you want to execute something on data, then those data must be loaded first. Then only you can perform some add instruction. Before loading the data, you cannot execute a add instruction. So communicating with memory is only through load and store instruction. Okay, so there are 3 types of memory interaction possible. First interaction is fetching the instruction. When you want to fetch the instruction, then also you need to go to memory, fetch the instruction. This is the first instant where you need to access a memory, and this is true for all the instruction. Any instruction you want to execute, first of all you need to fetch it from memory. So one memory access is required. But next, after that, if the instruction is load and stored, then you will go again to the memory to either to write a data or load a data, right? But if it is an add instruction, you no need to go to memory anymore. Only the fetch is enough. So there are 3 things. One is instruction fetch, then loading and storing. These are the 3 times when you will go to memory and will access the memory. Okay, so now let me now explain a store instruction. Store instruction is 1. Suppose the program counter value is 1012. If the program counter value is 1012, it means that it will fetch this instruction, store instruction. Store register 1, 8, register 0. So it's a store instruction. So fetch is done. Fetch ho gaya. Fetch done. After fetch, decode phase. In decode phase, it will understand that okay, it's a store instruction. Then it will also realize that okay, if it is a store instruction, then I need to first calculate the effective address, because store instruction, if we concentrate here, store means store the content of register 1 to this memory location. Okay, store the content of register 1. So it here will move the data from CPU to memory. So anyway, first thing is we need to calculate the effective address. So in the decode phase, if it is a store instruction, it will again realize that, okay, first I need to calculate the effective address. Effective address based on what? 8. So this 8 will be available here in this temporary register, and the content of register 0 will be available here in this temporary register. Okay, so this what is done in decode phase. Decode done. Then in execution phase, this 8 plus $0 will be performed, and your effective address is ready here after the execution phase. Effective address done. In memory phase, what we need to do now, we need to access with memory. But what to do now? In this phase, we need to store the content of this address, this register. We'll store the content of this register register 1 to the memory. Which memory? The memory address that is calculated in the effective address. Okay, so after this phase, a write back phase is not required in store, because write back phase is normally once the data is ready in CPU, inside the CPU, in which register we need to store it, which is not required in store. In store, we are moving data from register to memory. So in case of store, only fetch, decode, execute, and memory is required. So if this point is not clear, then please watch my video again. I will upload the recorded lecture. So you need to watch my lectures again and try to understand, why in case of add, memory access is not required, why in case of load all the stages are required, and why in case of store write back is not required. Try to understand it, and even if after watching my lecture, if it is not clear, then you can ask me question. I will clear your doubts. But don't worry, these concepts that I'm discussing here, these concepts will be discussed in more detail in your textbook. We'll spend at least 1 or 2 weeks to understand the detailed concept. But if you understand these basic concepts that I'm explaining here without much technical details, it will be very, very easy for you when you will read the textbook to understand it. And also the concept that I will discuss from those chapters. That's why I'm trying to give you a upper view of computer without following any textbook. Okay, so these are the 4 or 5 phases that normally the computer use to execute instruction: fetch, decode, execute, memory access, write back. That's it from this point. I'll discuss these points, as I said, more when we'll discuss the textbook. Okay, so this point is done. I hope it is clear. The point that is he mentioned here, I think I have explained this point in last class also. The machine understand only binary numbers. Why these instructions are written in text? These instructions are written in text to make our life simple, because I'm taking a class here, right? If instead of writing a store instruction, if I write 1 0 0 1 1 on like in binary format like this, then it will be difficult for you to understand also, and it will be difficult for me to explain also. That's why instead of explaining everything in binary, I have written directly the assembly language code here, and I'm executing it, and I'll assume this throughout the course also. But actually, every time you have to understand that ultimately every instruction is written in a 32-bit binary format, and these 32 bits are actually moving from memory to instruction registers. Okay, so the first part is done. Then there are some more important points that need to be discussed. The point is performance of a computer. So to performance of a computer, before discussing about performance of a computer, you need to understand these 3 terms. Application or program means, suppose you have a computer, or you have a laptop, or you have a mobile phone. So application means any program that you are. Suppose you are now playing a video file, in your computer. So suppose it is a VLC player where you are playing the video. So that VLC player is an application. Suppose at this moment I am using a PowerPoint slide. So the PowerPoint is an application. I am running a PowerPoint application in my computer. So why I'm explaining this here, because many time in this course I'll say that I'll let us run a application on this program, let us run a application on that program. So maybe you will confuse what is called application. Program is also application. Like if you write a matrix multiplication program and you are trying to execute this program, that is also a application. So you have to understand what is called application. And suppose you have 2 huge video files. Suppose one video file is of 5 GB, another video file is of 3 GB. You want to merge these 2 video files. That's why what you are doing, you are using a video file merger software. So that software is also application. You will run it, and then you will give this to video 1 and video 2, and then click merge, it will merge. So that is also an application, right? So and what is core? So core means the main processing element except the cache memory. So till now I have explained you a CPU. So inside the CPU there are registers, arithmetic logic unit, program counter. So everything you can consider as a core. Why I'm saying it's a core? Because modern days there are multiple cores inside a processor. So that part I'll not explain today. Maybe in my recorded lecture I'll explain why multi-core processors are required. So application programming code is important. Now we'll try to understand what is called performance. Suppose you have two computers, computer 1 and computer 2. You have two computers, and in both the computer you need to run an application. This is your application. Suppose the application is a very heavy application. As I said, assume that it's a video editing software. You have a huge video and you need to merge this video, 2-3 videos together. So this particular work you need to done in this particular application. Now for this you have two computers. In which computer you want to you have option to perform run this application in any of this computer. So now, or assume that you need to purchase this to computer. This is your job, that you need to run this particular application. And now you have option that either you want to go with C1 computer C1 or C2. So how you will check? The next question you'll say that which one will give me better performance, right? If the shopkeeper is saying that, sir, you have two options, which one you need to take? Then the next question you'll ask the shopkeeper is that, look, this is my requirement, I want to play a game or I want to do this video editing thing, so which computer will give me better performance? This will be your next question. So now here, in terms of as a student of computer architecture, first of all try to understand what do you understand by performance. Performance ka matlab kya hai? So a straightforward answer of performance is time. So if I run this application on C1, if it's take 20 seconds, and if I run the same application on C2 and it takes 25 seconds, then which one is better? C1 is better, right? Because it is faster. So there are many other parameters also, but I'll not discuss those today. But at least this is a parameter, right, to measure the performance. Execution time. Execution time is one of the most important parameter to measure performance. But this is not the only term. There are some other terms also there to measure the performance. So in this slide, we'll only assume execution time as performance. So consider there are two terms here. Performance X means performance of a computer X, and execution time X means execution time of computer X. What is called execution time here? Execution time means execution times is it is always with respect to a program or with respect to application. If you run a application on C1, then here I have written 20 seconds. So that 20 seconds is the execution time on C1 for application A. In the same way, if you run this application on C2 and it finishes in 25 seconds, then that 25 seconds is the execution time. Okay. So now performance and execution time are completely opposite, right? Because if you have you will understand it from here. So suppose the performance of computer X is higher than performance of computer Y. So you can see like this here, the performance of C1 is higher than performance of C2. It means that the execution time of this one, execution time of Y is more than execution time of X. You can see here. Okay, so I hope you in this slide at least you have understood the term understood the concept of performance in terms of execution time. Means जिसका execution जो जितना fast है वो उतना better है, and उसका performance उतना better है. So but in this course we'll understand that this is not the only thing that we need to check. There are some other important points also we need to check. Okay, so performance done. Now one more point here, CPU time. So normally CPU time means if you run an application to a program, how many time it takes in CPU. So at this moment maybe it will be difficult for you to differentiate between execution time and CPU time, because what I said in execution time, that if this is your computer and you have an application, you run the application in this computer, and if it is getting 20 second time to complete, then this is your execution time. And here I am saying CPU time. So CPU time, I'm saying that the total amount of time to run this application on this computer, total amount of time it spent on CPU. Okay, so here at this moment, I'll not explain the difference of CPU time and execution time. It will be clear in next week, I think. So but before understanding CPU time, you need to understand one important point. It's called clock cycle. So since in computer everything's a digital circuit, right? Maybe it's look like very complicated processor, but ultimately everything's a digital circuit. Internally, all are designed with transistors and gate. So you know that digital circuits executes or works on clock cycles, right? So suppose this is one clock cycle, and the next clock cycle will start from here. This is another clock cycle, then this is another clock cycle, and another clock cycle will start like this. So this is how clock cycle works, right? And if it is your digital circuit, then the digital circuit can work in every ages. Suppose in every cycle there are two ages. There is a positive age and there is a negative age, right? So in most of the digital circuit can trigger in both positive age or negative age. So the thing is that if this is a cycle, every cycle has fixed amount of time. So this is another cycle, right? Every cycle has fixed amount of time it takes. So that's why you normally processor speed are written in gigahertz. That means hertz means cycle per instruction, and gigacycle per instruction means gigahertz, right? So how many cycles is possible within a single second? Not cycle per instruction, cycle per second. Okay, so you need to understand the concept of cycle first. Why I'm saying cycle? Because suppose you want to calculate CPU time. When let me explain it in more detail. Suppose you want to run this application A on this computer and you want to calculate the CPU time. So how you will calculate the CPU time? First, you will try to find out that total CPU cycles required for this program. Means if you want to run application A on C1, how many cycles it took to execute it? So total cycles is coming out from here. Then if you know the total cycles, then how can you calculate the time? You can calculate time by using this, the time required for one cycle, right? I don't know what happened. Yeah. So here I said every cycle needs some time. So from this, if you somehow you know that how many cycles it took to execute a application, then you can multiply it with the clock cycle time. Means how many time the time of one clock cycle, then you can calculate the CPU time. So you can also calculate CPU time with this formula. CPU time is, if you know the cycles, total cycle required to execute a application, then you can divide it with clock rate also, and you will get the CPU time. Now there are two important terms here: instruction count and cycle per instruction. Instruction count is simple. If you know my previous, if you are following my lectures properly, I have explained that if you want to run a application, suppose this is your application A, you want to run it in computer, then you have to come the application must first of all you need to compile this application, and application ultimately must be in a format of instructions, right? It should be written in the form of assembly language program, right? So there will be this program A. Maybe it's written in Java, C, C++, doesn't matter. But ultimately, before running it on computer, there must be some instructions, like instruction 1, instruction 2, 2, 3, instruction N. It should be written in this format. So it means that if no matter how complex your application is, when you compile it, there will be a set of instruction, and that set of instruction is limited. It's not infinite. That is limited. So instruction count means when you will execute this application on a computer, how many instruction it will execute. So every time, it's not required that every time it will execute all the instruction written. Why? Because of jump instruction. If you remember when I was explaining program counter, I said that means after a jump instruction, it may jump to the next instruction also. It may go to some other instruction also, right? Or sometimes it may be possible that there is a for loop, and after this instruction, it will again move from this point to this point. But the number of instructions that will execute is fixed. It's fixed means the way I have said that if the program counter value is there, based on this program counter value, it will fetch an instruction and it will execute. So when you will execute an application on a CPU, the how many instruction you have executed, it is called instruction count. And cycle per instruction means the time or cycles required to execute one particular instruction is called CPI. Okay, now let me CPI means what? If CPI means if you know the CPU clock cycles required for a program, means suppose you have executed a complete application, and the complete application is A, and now you know this term, the total cycle required for this application, it is written here. This term you know. How can you calculate CPI? The other term that you need is instruction count. So if you know these two values, the total cycle required to execute A, and you also know the total instruction executed when I have executed A, then you can calculate CPI, which is cycle per instructions. The reverse is you'll try to calculate is instruction per cycle. This is the reverse of CPI. But both CPI and IPC are very, very important terms for this course. So whatever terms I'm discussing or whatever formula I'm discussing, I don't think that this is just an introduction lecture and this is not important. Whatever I'm discussing here are very, very important for this course. That's why I'm explaining it here. So the concept of clock, very important. What is called CPU time, important. What is instruction count, important. CPI, IPC, everything is important here. So now there is one more formula here. Suppose I want to calculate CPU time and I only know the instruction count, then what other parameters I need to know? Instruction count into CPI. Suppose instruction count and CPI both are there, then what extra thing we need? So from instruction count and CPI, what I can calculate from here? Total instructions are there and cycle per instruction is there. So this if I multiply these two terms, then I'll get the total CPU cycle required to execute this, right? Then means by multiplying these two, I'm getting this term. So I need to multiply this with clock cycle time again, and I'll get the CPU time. So I hope this part is clear. This point, these formulas and all we'll discuss again. We'll start discussing from textbook next week. I think it is already 2:50, so I think I need to stop here. There are some more concepts I need to discuss from cache memory before starting the actual course content. So what I'll do from this particular point, there are 3-4 more slides. So I'll do a recorded video and I'll upload it because there is one lecture pending. So for that lecture, I'll record this video. Oh, sorry, there are not one lecture, there are two lecture pending. The lectures of 5th January is also pending. So in one lecture, I will record from this slide. There are 3-4 more slides where I explain you the basic concept of cache memory that I will record. And in one more lecture, I will upload an interesting video that may not be directly related to your course, but that video will be on main memory. Main memory means how a main memory that is written here. Main memory means RAM, right? So how what is the internal structure of a RAM? How RAM store information, right? How if you want to store some data in a RAM, how this RAM is actually storing it. So all these things I'll discuss in another recorded video. So but that video will be not directly related to your course content. You can watch it if you are interested. But the first recorded video that I'll upload, it will be important, and in that lecture video I'll explain the concept of cache memory. I think I'll stop here again. Please share my message to all other that please maintain attendance. I can see only 60 students are here, but class strength is more than 90. I think 95. So attendance is, if you do like this, then I'll either stop uploading recorded lecture or I'll start taking attendance. I'm not taking attendance because it will waste my at least 5 to 10 minutes I will waste on taking just attendance. That's why I'm not taking it. Execution time in loading the application or time to execute task application. Execution time in loading is including both. That's why I said I am not. See, Mohit, you have written execution time to load the application or time to execute the task. There are two different things here, but since that's why first one you can say the total execution time, and second one is actually the CPU time. That's why I said I'll not explain it today. I'll explain it when I'll start discussing from the book. But since you have already mentioned it here, whatever you have written in your first line, the execution time to load, actually this is the total execution time, means loading plus execution, and only execution is the CPU time. Any other queries? then let me stop sharing. Why ME not required means? Okay. You are saying about memory access mem or mem is not required in stored. No, mem is required in stored. Mem is not required for add. Store and load are interacting with memory, right? And memory is the only stage through which you interact with memory. So mem is always required. A write back is not required in store. Try to understand it why write back is not required in store. Mem is common for both load and store. No other questions? I'm stopping the recording here.